Okay, once again, no one else is here online, but we're recording for you anyway. Hopefully he sticks around longer. Yeah, Homer, he's getting kind of tired, but I don't think he knows what else to do, so.
Yeah, I know. I don't know what would happen if he didn't have that. He'd be stuck at home with his dad. Bad shit. Oh, yeah, those two guys would probably two officers in one house like all day. I don't know if that's possible.
He'd have to do something else.
Well, there's no way when Boston was talking about his dad. I'm like, really? Like,
It's mind-blowing. Yeah, he's a nonagenarian in 90 something. Yeah,
he said 99. That's a good run.
His dad is 99?
Dad's 99.
All right.
Dad's still great in all of his astronomy exams, too.
All right, let's focus now on second-order circuits. You got to you might have to jump around a little more before coming to class because these take a lot of focus. Yeah. So we looked at the process of second-order circuits, the process of solving them, and the first step we found, well, of course, the second-order circuits form a second-order differential equation, and the steps in solving that are, you basically, I don't have that characteristic equation, but basically you propose that the solution is a sum of two exponentials with different decay rates, S1 and S2. And, you can set up the formula for S1 and S2. It's that characteristic equation when you take the second derivative of the exponential and the first derivative and the exponential itself adding up to 0. I've skipped that step. I don't know. I should probably add more stuff to this, but I hate to get too involved in the derivation. But the table, which we looked at yesterday, shows you the important information you need to know. And let me zoom in on this a little bit. And it kind of encapsulates the problem-solving process. Initially, you have to, initially you have to, well, it's not shown, it's funny, it only shows, it's not there anymore. It's a little flaky. Ah, there we go. I made it yellow. I think it might be easier to see through it if it's yellow. So the first step is you have to take the components and solve for what alpha and omega 0 is. That's the first thing in the table. You can't really go anywhere until you know what that is. And then once you know the comparison of the values between alpha and omega, you then you go down one of these three tracks. It's either going to be overdamped, underdamped, or critically damped. And then what happens is, if it's overdamped, the solution is A1 e to the S1t plus A2 e to the S2t. If it's underdamped, it's e to the minus alpha t times B1 cosine omega dt plus B2 sine omega dt. So that's the sinusoidal oscillation that takes place. And then if it's critically damped, it's just you have basically only one. Critically damped is when the square root term on the S1 calculation goes to 0. Omega 0 is alpha, is the same as alpha. And in that case, you only have one, decay on your exponential, but in return, you also have one of these components has a t multiplying it. So it's A1t e to the minus alpha t plus A2 e to the minus alpha t. And you've seen that, right? You did all this, I'm imagining, but I think everybody forgot that already. You forgot that was a long ancient history. Yeah. Oh, you did. Good. Yeah. So I'm not explaining this too much, but basically these are the different forms of the solutions. And in order to actually get the exact solution, you have to make sure that you have to choose the B1 and the B2 if it's underdamped, or the A1 or the A2 if it's overdamped. You have to choose those so that the boundary condition is met, so that the initial value of the current is correct, and the initial slope of the current is correct on your solution. So B1 and B2 will actually be pinned down now to make sure that it meets your boundary conditions.
What's the 0 plus?
This 0 plus means its time is still 0, but it's an instant after the switch has opened or closed. They're saying the switch is opening or closing at 0 usually, and they talk about 0 minus and 0 plus as being infinitesimally close to 0, but either right before or right after. That's what that means, and that allows us to make certain assumptions about I. So, for instance, I of 0 plus in the circuit, immediately after the switch has closed or whatever, or opened, whatever it is. It's going to be the same as I of 0 minus because the current through an inductor can't change. That helps us with the boundary. Well, it's whatever the switch is doing. Sometimes the switch opens, sometimes it closes. But it's the instant after the switch has moved its position. The switch moves at t0, at time 0, and then at the instant after that is what you're looking at for 0 plus. That's your boundary condition for before that, because technically it's kind of, there's a sort of a weird, what's happening exactly at 0 is kind of weird when a switch is closing. Ollie?
So IFC
as a function of time. So we're solving for the behavior of the current as a function of time. As the energy is dissipating, sometimes it's transferring from one to the other, oscillating back and forth, or dissipating out through the resistor. Yeah, and it's either going to be oscillating, or it's going to be just an exponential decay, or an exponential decay with a scale times t involved in it. And it's just picking out the form that you, so the basic idea is you find alpha and omega 0, you figure out which form it's going to be, and then you got to match the boundary conditions. And the boundary condition matching is the tricky part, because that's what determines the A1 and the A2. And the rationale that we use to form the boundary conditions is that's that hand-wavy kind of thing I was doing at the end of the lecture on yesterday. And we'll just we'll finish yesterday's problem, and then we'll solve some more. So Lisa, I don't know if you picked up yesterday's lecture, but the PDFs you can look at show you the solution that we developed. So we did example 1 where we're solving for basically omega 0 and alpha, and then figuring out what the damping is, and then solving for S1 and S2 using the table. And we did another example, again, finding the alphas and omega 0s. That's the easiest part of the whole process. And then yesterday what we did is we found alpha and omega 0, and figured out, in this case, it's an underdamped circuit, and omega d, which is the square root of omega 0 squared minus alpha squared. That's the oscillation. That's going to be the oscillation of the sinusoidal response part, is 1.658. And then step 2 is now that the lengthy process of solving for the initial conditions. And we need to find IL at 0 plus, and we need to find DIL dt at 0 plus, the slope of the current and the current itself at that instant after the switch has moved. And our explanation is that IL at that time, 0 plus, is going to be the exact same thing as IL before the switch moved. And IL before the switch moved is when the inductor is in the steady state. We assume that the circuit has been at rest for a long time before the switch moves. So whatever oscillations have happened have damped out exponentially, they've gone to 0. So IL has, the inductor has become a short circuit. And so I drew a short through the circuit there to show that here. This is the inductor. I drew that short there to show that it was a short when it was connected to a 50-volt source. And so that means the current going through that inductor at time 0 was 5 amps, because you had 50 volts going over 10 ohms. And that part is pretty easy. Well, the other thing to realize is that the capacitor voltage is 0 as well. Well, actually, no, it isn't really defined, because it's floating here. You don't really know what that voltage is. It could have been anything. And they didn't. So I actually added that statement here: the capacitor is uncharged. It wasn't in your handout, which means the capacitor voltage is initially 0 as well. These things all come into play when you're forming that that initial condition for the slope. So DIL dt, based on the inductor law, is VL equals LDI dt. So we can actually solve. Hey Ben, we can actually solve for DIL dt as being VL over L. And so the initial slope, that's what DIL dt of 0 is. I'll go back to red here. So finding this initial slope of the current, we're going to use the inductor law and say, well, the initial slope of the current is just going to be the voltage across the inductor divided by the inductance. So to find that initial voltage across the inductor, that's the tricky part. And this is what Clio actually recommends. I really like this approach. You redraw the circuit at 0 plus, this instant after the switch has moved, and you replace the inductor with a current source of its initial current value, and the capacitor is replaced with a voltage source with its initial value. And then you can use KVL to solve for the voltage drop across the. And in this case, we find that the voltage drop across the inductor has to be minus 25 volts using KVL. And so we ended up being right at this point. We solved for that. And now we have to go back to the table and use that information to solve for B1 and B2. And according to the table, if you look at your table, what's B2? We're going to see the table now. Knowing what I've done here, what's B1? Let's just start with B1. What's B1? Yeah, according to the table, on your table, it says B1 is IL 0 plus, right? Which we've decided is 5 amps. And B2 is, well, actually, what is the formula involving? There's the second formula there. What's that second formula say? Minus alpha B1, right? plus omega d b2. And where did that come from, by the way? I mean, it came from the table, but why is it on that? What does that mean? If you differentiate this this expression, you take the derivative of this thing, it's minus alpha, right? You first take the derivative of the exponential, right? It's minus alpha e to the minus alpha t times b1 cosine omega t, blah, 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 plus e to the minus alpha t times the derivative of the cosine, which is minus b1 sine, right? And plus b2 times the derivative of the sine, which is b2 cosine. Now, at 0, the sines go to 0, and the exponential goes to 1. And at 0, the derivative of this expression reduces to just minus alpha b1 plus wd b2, because the exponential went to 1, the sine went to 0, and that's all you had left. And that's what this actually, that's where that comes from. You guys look like you'd really like to see me derive this. Okay, well, I'll see if I can find something maybe for tomorrow. I don't want to drive it, but it's very tedious to kind of show that. If you look at for the overdamp, it's a little bit easier to see, right? The derivative of this thing is going to be S1A1 e to the S1t plus S2A2 e to the S2t, right? And when you set t equal to 0, that's just S1A1 plus S2A2. You see that? That's why it says that right there. Okay? And it's the same thing for the sinusoidal, it's just a little more complicated. And the same thing for the critical one. It's just a little bit different as well. So you can prove that to yourself if you don't do it. Yep. It's the slope of the current. It's not the derivative for all time. It's just the derivative at t equals 0. The slope at t equals 0 of the current. In other words, what is that slope? Is it a really steep ramping up current, or is it 0? Is it perfectly flat? Depending on the way the circuit is set up, sometimes it's going to be a slope of 0 initially, and then it shoots up, or sometimes it's going to be shooting up and then it kind of angles back down. You don't know until you've actually solved for your initial conditions. And we found that in our case, this the initial slope here, what it's saying is that, so basically what we found by these boundary conditions is we found that the initial I at 0 is going to be 5 amps. And we've also found that the initial slope is going to be minus 25 amps per second. So if I was going to sketch the solution as I understand it at this point of IL of t, all I know is that at t equals 0, it's at 5 amps, right? And it's shooting down at negative 25 amps per second, something like that. That's all I know, right? It's actually just, it's heading down. You're not with me at all. This is problem number 2, source-free series RLC. Okay. I know these are a nightmare. I have a nightmare about them myself, but I've done this enough. It's not that big of a deal. I will tell you that the nightmare becomes not so bad once you've done it a few times. So anyway, minus alpha b1 plus wdb2 is the same thing as the dIL dt at 0 plus. Scrolling this on here. You should be writing these answers on your sheet. That's why I printed them out for you. And that equals minus 25 amps per second. Okay. You can. That's fun. You can watch it or look at it on the PDFs too. Minus 25 amps per second. That's the IL dt at 0 plus. And so basically the first equation already gave us the answer for V1. It says B1 is going to be 5, right? That's what B1 is. And now we're just going to find alpha B1 plus WDB2 and set that equal to minus 25. Well, since we already know that the B1 is 5, and we know that alpha is 2.5, so then we're just going to write, well, minus 2.5 times B1, which is 5, plus WD, which we found out on the last slide was 1.658, times B2 is going to equal minus 25. And so therefore, B2 equals minus 12.5 over 1.658 equals minus 7.539. And then the last part is you just compile the solution. We've got all the parts now. We've got V1, V2. We know the form of the solution. So the last step, I've run out of room here, is to compile the solution. And that means this. I'm not even going to write it. It's the same thing that you see at the bottom there. Because we just found out that, well, if you look at your table, right, it says the solution is e to the minus alpha t, right? See your table? And times b1. This is b1, right? Cosine omega dt plus b2, which is negative 7.9. This is b2 sine of omega dt, right? So you've got all those parts, and you just assemble them into the formula based on what the table says. Yeah, at one point I was actually thinking of just getting rid of second-order circuits from the whole class, but it's part of the kind of part of the requirement. it's part of the thing, unfortunately. And what's fun is, and what I like about this having MATLAB and everything is you can plot these things. And here I'm plotting it in FreeMat. I'm making a t vector that goes from 0 to 4, and my f, really this should be I, but it's just a function. E to the minus alpha t times 5 cosine, b1 cosine omega dt minus b2 cosine whatever. And this is what it actually looks like. And you can see this is your initial condition, right? Here we are at 5, and we're shooting straight down, negative 25, that was the slope. And then you get this sort of sinusoidal damping, which damps out pretty fast. A sinusoidal oscillation, which damps out pretty fast. And also, in the next slide, I'm plotting the derivative. And this is actually a quick and dirty way to calculate the derivative in MATLAB, which don't worry about it. But you can see that the derivative starts at minus 25, which is what we said it was supposed to, and then eventually goes out to 0. Those are the two boundary conditions we had to establish. Okay, we made it through one. Now, I'm hoping we can do another one by the end of the class today, because again, if you see it a couple times, you kind of want to get the whole thing down. And then we'll focus on the difficult part near the end, which is those boundary conditions. Well, the real tricky part is, I think the trickiest part is doing the boundary conditions, and figuring out what those things are. And in fact, that I end up, because the problem solving one of these things takes so much time, and there's so many ways you can make a mistake. There's a good way to break it up in terms of like a test question. You might just be asked to find what are the initial conditions for this circuit, and that's a relatively easy thing to focus on, or at least it's a focused thing to work on as opposed to the scattering of the solution in general. So again, the same logic applies to parallel RLC circuits. And here we have all the components connected in parallel. And, again, it's the same type of analysis, I of t. Well, actually, they're defining initial I. And, well, you can derive the differential equation by applying KCL here at the top node and summing all the currents leaving that node. If the node voltage is V, the current going through the resistor is V over R. The current going through the inductor is 1 over L times the integral of V dt. That's the integral, everything that happened from minus infinity to t, plus the capacitor law I equals C dV dt, all have to add up to 0. You do another differential step here, and you get this second order equation. But it's a little bit different than the one for the series RLC. The difference being we're actually expressing the solution in terms of the voltage instead of the current. Right? With the series RLC, the controlling variable we were using was the current. With the parallel RLC, the controlling variable is going to be the voltage. And alpha is different. Alpha for the parallel is 1 over 2 RC, whereas for the series, it's what is it again? It's R over 2L or something? Or yes. Yeah. Okay. And omega 0 is the same. So this is the same as the series. And as with the as with the other series one, we have these three different possible types of solutions. You can be overdamped, critically damped, or underdamped. And the equation has the same form, which is nice. So it's it's the same process of finding the solution. Once you actually find those those terms alpha and omega zero, and you figure out which way to go. You just go through it, go ahead and go step through it. So here we are, number 3. Let's try it again. And again, the process is to, the first thing we're always going to do is, to start off, is we always have to find alpha and omega zero. Yes. Okay, so alpha is, again, on, this is a parallel, right? And you can tell it's a parallel circuit because of the way those components are arranged, right? And the switch is opening at time 0, meaning it's a natural response. It's a source-free response because we're removing the source at t equals 0. So alpha is 1 over 2 RC, and R is 20, and C is 0.004, so it's 1 over 2 times 20 times 0.004, which is, sorry? Yeah, which is 6.25. Yep, that's why you gotta make sure you're on the right table. We're now using table 2. Just for people who might be watching online. This is table 1, and this is what we use for problem number 2. Now for problem number 3, we're using table number 2, which is the step response. Oops, that's the step response of the series RLC. So it's actually going to be table 3, which is the natural response of the parallel RLC. And it's all the same. Here's alpha, here's omega 0, and we just calculated alpha, but anyway, we'll just follow these steps and grind through it. It's basically just a grind. I wish it was more exciting, but this is circuits. So so omega 0 is still 1 over LC square root of, and that means 1 over the square root of 10 times 0.004. Going to raise that to the 1/2 power, which turns out to be 5. And because alpha is greater than omega 0 in this case, now we are actually overdamped. I'm sorry? Yeah, alpha is 1 over 2 RC. So we are overdamped. And according to the table, what does the table say for S1 and S2? So look at table 3. Yeah, so S1 equals minus alpha plus the square root of alpha squared minus omega 0 squared. And that equals minus 6.25, oops, 6.25. Plus, and it turns out the square root of alpha squared minus omega 0 squared is going to be 3.75. And so that equals minus 2.5. Barely squeeze it in there. I'll write that a little bit bigger. Minus 2.5. S2 is minus alpha minus the square root of that, and so it's minus 6.25 minus 3.75, which is going to equal minus 10. Okay, then the nasty step 2, solve for the initial conditions. And the initial conditions we need to solve for in the parallel circuit are, according to the table, you can see a V of 0 plus and d V dt of 0 plus. So we need to find the initial voltage and the initial slope on the voltage after that switch has thrown. So for A, again, sometimes you can do these by inspection, and sometimes it's a little bit tricky. But imagine now, before the switch has opened, you know, what's going on in that circuit? What's the steady state, you know, what's a steady state circuit going to be like? This is the tricky part, right? So, the capacitor's a short, right? The inductor's going to be a short, and the capacitor's going to be an open, right? Okay. Can you now figure out what those? So then, what's the voltage going to be across the capacitor? Okay, the inductor's a short, and the capacitor's an open. And all the current's going through what? The inductor. Because the inductor's a short. The current's going to follow the path of least resistance, right? Now, if you're confused by that step, you can always draw the circuit here at t equals 0 minus. T equals 0 minus. Everything's in the steady state. You've got a 2 amp source going through a parallel network of 20 ohms, a short, right? That's your inductor, and an open, that's your capacitor. And what we're trying to find is V of 0 minus, right? And what is that? Well, pretty easy when you redraw the circuit, right? You're measuring the voltage across a short circuit. Yeah. Yeah. So I recommend doing that. It's not hard to redraw the circuit and just change all the, you know, all of the inductors and capacitors to their steady state behavior. So capacitors an open, inductors a short. So so t equals 0 minus, the C is an open circuit, and the L is a short circuit. Okay, and V of 0 minus is going to equal 0 volts. And that's really nice because now we can say, okay, well then V of 0 plus, because it's a capacitor, you can't have a step in the voltage across the capacitor. So it's by default, V of 0 plus is going to be the same as V of 0 minus, which is going to be 0 volts. Okay, and that's because of the capacitor there. It can't, yeah. Can't have a step across the capacitor voltage. Now, what about IL of 0 plus? So that would be this, oops, that would be this right here. Or IL of 0 minus. What's IL of 0 minus?
0.
Sorry? 2 amps? Yeah. It's 2 amps, right? Because all the current's going to go through that inductor, right? So IL of 0 minus is, or in other words, IL of 0 plus, because of the inductor, is going to be the same as IL of 0 minus, because it can't change instantaneously, which is going to be 2 amps. It's getting all the current flowing through that short. Okay, that part's usually pretty easy, but we also now have to find dV dt of 0 plus. So finding that is, so for B, okay, we have to find dV dt of 0 plus. Now the capacitor law says that IC equals C dV dt, right? And so therefore, dV dt at 0 plus is just going to be IC over C, where you take the IC of 0 plus. Okay, so if we can find the current flowing into that capacitor at 0 plus, then we can find the slope of that voltage. Again, that's the boundary condition on the differential equation. We need to know the voltage, the initial voltage, and its slope to be able to pin down the exact, coefficients for that solution. Okay, And here again, this is the Clio. This is the really cool Clio thing. We're going to redraw the circuit. Oops, too many. Redraw the circuit at t equals 0 plus. But now the L is going to be replaced by a current source of I0, and the C is going to be replaced by a voltage source of V0. This is actually, this makes it so much easier if you do it this way. So the source is gone because the switch has removed it, but now that inductor is going to be replaced by a 2 amp source. And the capacitor is going to be replaced by a 0 volt source. And what we have to find the slope on the voltage is IC of 0 plus. This is t equals 0 plus. Okay? So how do we find what's going on in that circuit? This is the hand-wavy part of the whole process. Okay? This is the one it's an art form in a way, but there is a logic to this. You have to we have to reason our way to finding out what is that current at 0 plus, the current flowing into that capacitor. Why? Why 2 amps?
Because it wants to maintain each of the branches.
Yeah. Do you get what Chris is saying? He's saying that, okay, so the voltage can't change. In other words, we've got a 0 volts imposed across this whole parallel network. That means the voltage drop across the resistor is also 0 volts, right? So how much current is going to flow through the resistor? Nothing, right? So where does all that 2 amps go? It flows right into the capacitor. Okay, now if the initial capacitor was like, say, 10 volts, then you couldn't say that. Then some of the current would be going through the resistor, and then some of the current would be going through the capacitor. And you could solve that, using Ohm's law or whatever. But it's negative, good. Yep, because that current, that 2 amp current, can't go left because it's 0 volts there, but it can go into the capacitor, which it will. And so IC of 0 is, and it's really kind of just KCL that's doing that for us. IC of 0 plus has to be minus 2 amps. Okay, so that's a really nice step that you can do. I recommend you do that for all of these because it's so tricky to get the right answer. And so therefore dV dt at 0 plus, I don't really have to say VC because it's the same voltage across all of those elements. dV dt at 0 plus is then just going to be IC of 0 plus over C, which is going to be minus 2 over whatever C is, 0.004 farads, which is going to give us minus 500 volts per second. This stuff is happening really fast, so that rate is really high. Minus 500 volts per second. Okay, and that's the last. That's the only thing. I think the whole process where most people are going to run into the difficulties. That's step B on step 2B. Yeah, that's just the most problematic in terms of understanding what's happening. And you just have to take that really carefully and draw that circuit and make those reasoning steps if you can. And then once you have that, then you just have to solve for A1 and A2 using the table. This is actually table 3. Okay, so what are the formulas there on the table for me? Someone want to read that off? So A1, what does the formula say? Yeah, V of 0 plus equals A1 plus A2, and we decided that V of 0 plus is 0, right? So therefore, A1 is going to equal minus A2. And what's the other formula say?
Oh, the dV step that we just solved for?
Yeah, dV dt of 0 plus equals
A1 plus A2 A2.
Yep. And S1 was, well, we know that that equals minus 500. And S1 is minus 2.5, so minus 2.5 A1, and S2 is minus 10, so minus 10 A2. Chris, thanks for joining us. Nice of you to drop in. Okay, but since A1 equals minus A2, we can actually plug that into there. And so then we can actually say that a little bit of algebra here, 10A1 minus 2.5 A1 equals minus 500. And therefore 7.5 A1 equals minus 500. And therefore A1 equals minus 66.67, and A2 equals 66.67. Okay, and then step 4, you assemble the final solution. So that's just putting all the pieces together. So V of t equals A1 e to the S1t plus A2 e to the S2t, and that's just basically that there, with a little bit of manipulation to get that. Okay, and it's also fun to plot what that looks like. I just like to see that. So this is the solution for the voltage. Okay, questions? 2B. Yeah, that's the tricky part. 2A can be sometimes a little tricky too, but 2A and 2B is that core. Yeah. Everything else is pretty mechanical. So we'll focus on some problems on that. In fact, we have a couple minutes. Maybe we can scroll down to the, yeah, if you look at problem number 6 on your handout, these are the kinds of things. And then number 7, actually I think number 7 is a little more relevant. Let's look at number 7, and then we'll look at number 6 maybe. For both, the inductor current and voltage determine their initial values, the initial values of their derivatives, and their final values. Eventually, when we do the step response, we're going to do that tomorrow, you have to know what the final value of these things are as well. The capacitor has 9 joules of stored energy before the switch closes. Okay. So this is the kind of problem, it's sort of a second order problem, but you don't have to do the whole solution. You just have to find what are the initial conditions and the final values of those things. So starting with the capacitor, we can just do that step pretty easily. WC equals 9 joules. And we know that that's CV squared over 2, right? That's the energy formula for the capacitor. And the capacitance is 0.5 farads, so it's 0.5 times VC squared over 2, which is, well, that implies that VC, doing a little manipulation, VC equals 9 times 4. So it's, let's see, VC squared is 9 times 4, so VC equals 6 volts. That's just a silly step to make you do a little bit of extra calculation on the capacitor. So the initial capacitor voltage is 9 volts. Now, usually finding the initial value on these things is not so hard. Okay, what do you think? So let's start with the current through the inductor. What's the initial current going through the inductor? Yeah, so we're in the steady state before that switch closes, and the inductor has become a short circuit. And so nothing's going to flow through the resistor. So IL 0 plus is 2 amps. Okay. What about yeah, because the inductor has become a short, it's going to just take all that current flowing through it. What about dIL dt? What's the slope on that inductor at 0 plus? Okay, don't read the answer. Okay. How do you know? How do we find the slope of that current? No, it's that same step we did in the last thing. So how do we know what the derivative of that current is? We want to find the derivative of the current at t equals 0. What is it going to be? We have to use some other variable to figure that out. Okay, just go look back at your labs again. Didn't get anything from that. Go ahead, say it again. Yes, it's the voltage across the inductor divided by the inductance, right? That's what we did right. No, in the one here. In this one we did here. In the first one we did it. Number 2. We said dIL dt of 0 is VL over L. And in your formula it shows that too. If you can look at table, this would be, well, it's a step response. I'm kind of going a little bit ahead here, a little bit out of order here. But it applies, right? dIL dt of 0 plus equals VL of 0 plus over L. And what is the voltage across the inductor after the switch opens? After the switch closes. After the switch closes, what's the voltage across the inductor? It's 6 volts because that capacitor voltage is switching in now, right? And that capacitor voltage, it's not going to change instantaneously because the capacitor can't have an instantaneous change on its voltage. So when we switch that capacitor in, it automatically instantly bumps up the voltage across the inductor to 6 volts. And this is where I recommend, you can draw the circuit there at t equals 0 plus, and you can see that you've got a 0.6 ohm here, and you've got the current source is doing its thing at 2 amps, and the inductor is kind of like a current source because it's going to have that same current it had before the switch changed, and the capacitor, which is now switched in there, is like a 6 volt voltage source. And VL is what determines the initial slope on that current. So dIL dt of 0 plus is VL over L of 0 plus, which is VC of 0 plus over L, which is 6 over 0.1, which is 60 amps per second. And what is the final value of the current? After everything is settled down again, now that circuit in that parallel configuration, what's going to happen in that infinity? What do you think is going to happen to the inductor current? After everything settles down again, the inductor has become a short once more. The capacitor has become an open circuit once more. So all the current flows through the inductor once again. So IL of infinity is going to just be 2 amps. Well, we know the initial voltage, DC, across the capacitor is 6 volts. What's the slope on the voltage? What's dVC dt of 0 plus? Well, that's using the capacitor law. It's IC over C, right? It's IC of 0 plus over C. And what's the current going through that inductor? What's the current going into the capacitor at 0 plus? Mm-hmm. Yeah. Mm-hmm. Okay. So, right, we're still here at t equals 0 plus, and so what's the current going through that 0.6 ohm resistor? Mm-hmm. 10 amps, right? You've got 2 amps going up, 2 amps going down. These are basically canceling each other out. So what's the current IC then? What's IC here? According to KCL, IC is what?
Minus 10 amps.
Right? It's going to be minus 10 amps. But the only thing that can provide the 10 amps is that capacitor, right? So the current's going to be leaving the capacitor and flowing into the resistor. So it's minus 10 over C, which is 0.5. So So dVdt is minus 20 volts per second. And then what's the final voltage value? What's Vc of infinity? Just reasoning it out. Don't look at the answer.
Well, your inductor voltage is going to be 0.
The inductor is short, the capacitor is an open. Yeah, the capacitor is measuring the voltage across the short of the inductor, so it's going to be 0. Mm-hmm. Okay. Well, we'll say it a little bit later, but that's the kind of thing, and we'll be doing step response tomorrow. Does anyone have any questions on assignment 7 or whatever, or 8, whatever you're working on? 7. Did you want to bring that up before we wrap it up?
Are you going to have the office hours on Friday?
Yeah, I'm here from 3 to 6 in the afternoon. Yeah.
So, I got most of these right. I got that one not right. I checked all these on the things. I got those right. I think, I don't know if I got that one right.
Assignment 7?
Yeah. And, I don't know if I got the C's correct. Got these right. I haven't done 8. Actually, I haven't really worked too much on 8 yet, to be honest, so.
So, do you have a question then, or?
Yeah. How do I find C on these here? Don't I have to set it to 0? You have to take you have to derive it and then set it to 0, I thought.
The maximum energy stored. So you did D?
Yeah.
Yeah. So, but here's a sine wave. What's the maximum value of a sine wave?
It's going to be the.
What's the largest?
1.
Yeah.
So it's just 1?
It's just 1 times whatever else is there. You know, the largest value of this can be is 1.
So 0.025.
Basically.
This is it.
Yeah. I guess so. Did that
So
work?
that's it?
Probably.
I don't know. I haven't tried it.
Yeah.
That 0.025 was the answer for number B.
Mm-hmm. Yeah. So what's the largest value? It was 0.025.
So.
Mm-hmm.
Okay.
Yeah.
I, had him help me, and we did all this algebra.
Well, you could, but that's a lot of work.
Yeah. Okay, so that's going to be the same for this.
Mm-hmm.
Okay.
Yep.
And then plotting these things here, I just tried to do it in Wolfram.
Yeah, it's pretty easy.
Is it?
Yeah.
It looked really weird. It almost looked like a solid blue chunk with some very little sprinkles.
Okay, what's the formula? You want to plot?
Mm-hmm.
And what's the formula?
Well, it said you wanted to plot all of them, right?
All right. Well, let's plot.
Okay.
Let's plot the energy. Or what do you want to plot?
This one here, 5 sine of 400 T.
Okay. 5 sine of 400 T from 0 to 5 pi.
Yeah. Yeah, that's what I got. That's correct?
It's 5 pi milliseconds. So that's actually, it's 5 pi divided by 1,000. It's in milliseconds, sorry.
That's why I look weird. Well,
Does it say
okay.
milliseconds?
No, it does. It does. It does right here. Right there.
Yeah.
But I didn't know how to get it to do that on there.
Yeah.
I
Milliseconds.
tried just having MS, but I didn't think I could do that.
Yeah.
Divided by 1,000.
So that's the, whatever that is.
Okay, so.
That's the energy?
Yeah, so you want me to plot all
all
these?
Yeah, just copy and paste them on the
Okay.
Word.
And then, okay, I could probably figure this out here. To be honest, I got stuck on this.
Yeah, it's just kind of tedious. This is a more fun one,
Okay.
and it's more educational.
I think I'll probably be able to figure this one out
Yeah.
if I just read some more into the chapter.
Yeah.
Okay. Yeah, I just get getting hung up on this one here on these C's, and I don't know.
Yeah. Yeah.
Okay.
I know. Sorry.
All right.